Section 14.4 covers two main ideas. The first one is tangent planes, and then the second one is linear approximations. And that is involved with something called the total differential. So we'll probably talk about that tomorrow. Okay, so we're going to start out by talking about how you saw this idea in calc last year. If we consider the graph of a two-dimensional differentiable function, if we choose a point and we zoom in on that point a lot, what is the graph going to look like? Yeah, the tangent line. And so what you did in calc before is you would approximate the function using that tangent line when you were really close to that point. Do you remember that? Vaguely? Okay, so we can approximate the function. Using a line. And last year you were probably told you're only going to approximate that function when you were sufficiently close to the point. You don't want to go too far away. You remember that? Farther away you get, the more inaccurate your line is going to be as a prediction. Okay, so here's what we're going to talk about today then. We are looking at 3D differentiable functions. If we pick a point on our three-dimensional function and we zoom in a lot, no longer looks like a line. What does it look like? A plane. Yeah. So now the surface really close to that point is going to look like the tangent plane. So the idea today is if we can find the equation of the tangent plane, we can use it to approximate the value of z or f, whatever we're calling it, when we're really close to that point that we're using. So the first question is, how are we going to find this? Okay, so here's the main idea. We are going to find two tangent lines. The tangent plane, then, will contain both of those lines. So we're going to find two tangent lines. The tangent plane will contain both of those lines. So the question then is, what tangent lines are we looking for? We talked about when we looked at limits, there's infinitely many paths that approach that limit or that point. There are infinitely many tangent lines, but there are two that are going to be the most efficient for us to find. We are going to find the two lines that result when we intersect our function, which I'm going to call z is f of xy, with the planes y equals y naught and x equals x naught. So x naught, y naught, z naught is going to be the point that we are interested in. So we are going to take the planes x equals x naught, y equals y naught, intersect those with our surface. We're going to have two tangent lines, which we are then going to use to find the equation of the plane. I'm not going to draw you guys a picture because you always make fun of my pictures, so I'll show you a picture. This is in your book. So let's say this is the point that we're interested in. We're going to have one line, other line, and then that yellow plane, that's the tangent plane. With me? Okay, great. So then, here's the equation of our plane. That's the general equation of a plane. We have A times the quantity x minus x naught times B, or plus B times the quantity y minus y naught, at c times the quantity z minus z naught equals 0. And we said that x naught, y naught, z naught is the, bless you, is the specific point that we're interested in. We're going to rearrange this a little bit. I'm going to put z minus z naught on the left side. So I'm going to move everything over and divide by c. I get negative a over c times the quantity x minus x naught minus b over c times the quantity y minus y naught. A over c is some constant. B over c is some constant. So let's make it a little bit easier. I'm going to call this one little a and this one little b. So our general equation is z minus z naught equals a times x minus x naught plus b times y minus y naught. Now, that's the general equation of the plane that we're interested in. Question is, how do we find the a and b? All this stuff that we've done with the plane so far, that's just a general plane. So we haven't taken into account yet our two tangent lines. So now, we need to use the two tangent lines. First tangent line, I'm going to call T1. And that's the line that results from intersecting the plane y equals y naught with our surface. If y equals y naught, that term in the plane is going to go to 0. So we'll be left with z minus z naught equals a times the quantity x minus x naught. You should recognize this. This is the equation of a line in point-slope form. A is the slope. Any idea what that slope is? Thinking about what you did yesterday? F of partial derivative with respect to x. Yeah. Yeah, so then similar idea. If we find the second tangent line, which is when we intersect the plane x equals x naught with the surface. Using this up above, if x equals x naught, that term will go away. So we get z minus z naught equals b times the quantity y minus y naught. This is also a line in point-slope form. This then will be the partial derivative with respect to y at that point. All of this brings us to the equation of the tangent plane. So, equation of the tangent plane is z minus z naught. All the way up here, we have that a and b, so we're using this, but now replacing a and b with what we found them to be. So we get z minus z naught equals partial derivative with respect to x at the point x naught, y naught, times the quantity x minus x naught. And then it's plus b, but we found b to be the partial derivative with respect to y at x naught, y naught. So that whole thing is the equation of the tangent plane. That's a, that's b. So you don't have to go through the derivation every time as to how to get that. You can just memorize it. But I did want to show you where that came from. Questions before we do an example? Okay, so we are going to find the tangent plane. To the surface with the equation z equals 2x squared add y squared at the point 1, 1, 3. Before we do anything, what is this surface if we were to graph it? A what? Right, an elliptic paraboloid. So our f of xy, that's just z. So that'll be 2x squared plus y squared. We need the first partial with respect to x. We need the first partial with respect to y. If we take the partial with respect to x, we get 4x. Partial with respect to y, we get 2y. We need to evaluate both of those at the point 1, 1. So we get 4 and 2. Then we're ready to write the equation of the tangent plane using this up above. X naught is 1, y naught is 1, z naught is 3. So we get z minus 3 equals 4 times the quantity x minus 1 plus 2 times the quantity y minus 1. Perfectly okay if you leave it in that form. If you decide you want to put it in standard form, you get 4x plus 2y minus 3. Either of those forms work. Questions about finding the tangent plane? Okay, here's why we're going to do it. Can I cover this up for a minute? Okay, again, I'm not going to draw a figure for you. I'm just going to have you look up here. Okay, this right here is that surface. This is the tangent plane. As you go from picture A to B to C, do you see that we're zooming in more and more? Okay, the further you get zoomed in, do you see that the surface is almost the same as the tangent plane? So the idea that we're going to use now is we're going to find this tangent plane so that we can approximate the value of z at points that are close to 1, 1. Kind of like you did last year in 2D, now we're just doing it in 3D. With me? Okay, great. That's what we're going to do now then. Questions about tangent plane before we talk about using the tangent plane? Okay, so the next topic of discussion is linear approximations. So in that example number 1 that we just did, the linear function, or the tangent plane, that tangent plane that we got is 4x plus 2y minus 3. Often that'll be denoted L. So that function is a good approximation of f of xy for xy that are near 1, 1. For example, if I wanted to approximate f of 1.1 comma 0.95, that point is pretty close to 1, 1, so I could plug it into that tangent plane that I got. So it would be 4 times 1.1 plus 2 times 0.95 minus 3, which is actually 3.3. So we're going to guess that the z value when x is 1.1 and y is 0.95 is about 3.3. If you actually plug that in to the original function you were given, you get 3.3225. Bless you. So we can see that our approximation is pretty close to the true value. L then, this function up here, is called the linearization of f at the point 1, 1. So the linearization at 1, 1. The approximation itself is called, so this approximation is called a linear approximation. Or you could see it referred to as the tangent plane approximation. Of f at the point 1, 1. So before we do an example, we're going to write out exactly what those look like. So this all relates back to the tangent plane, so we're going to rewrite that equation. So then, the linearization of f at some point AB. So linearization is the equation of the tangent plane, but we want it solved in terms of z. So it's going to be L of xy. If we move z naught over, that's really f of AB. And then you're plugging in A and B here. Okay. I hope you can see that these two are essentially the same. They're just written a little bit differently. Do you all see that? The linear approximation, then, is the actual estimate. So linear approximation is when you approximate f of xy using that linearization. Here's the catch, though. This only works if f of xy is differentiable at the point AB. So what should your next logical question be then? If this only works if f of xy is differentiable at AB, what should you ask next? Yeah, how do we know if f of xy is differentiable at AB? That brings up our next definition. We got like a definition and a theorem, and then we'll move on to another example. Let's say that z is f of xy. Then f is differentiable at the point AB if delta z can be expressed in the form that follows. Delta z equals the partial derivative of x at AB delta x plus the partial derivative of y at AB delta y plus epsilon 1 delta x plus epsilon 2 delta y. Where? Epsilon 1 and epsilon 2 go to 0 as delta x and delta y go to 0. Okay, so here's the good news. I have to show you that just so that you've seen it, and then I'm going to show you what actually applies to us. So we're not actually going to use this. We're going to use this theorem instead. What comes from this theorem? If f of x and f of y exist near AB, and are continuous at AB, then f is differentiable at AB. So you're going to have to look at the two partials, make sure that they both exist at that point, make sure they're both continuous at that point, and then we can say our function is differentiable at that point. The same is true if you have more than two variables. So if you're looking at a function of 3 variables, 4 variables, the same idea applies. Okay, that was a lot of writing, so let's do an example so that you guys can see exactly what I expect of you. We are going to show that the function f of xy equals xe to the xy is differentiable at 1, 0. And then we are going to find its linearization Then we are going to use that linearization to approximate f of 1.1 comma negative 0.1. We got to do two things. Show that the function is differentiable, find the linearization, and then use it to approximate. Okay, f of xy is equal to xe to the xy. From that theorem above, in order to show that f is differentiable at 1, 0, what we're going to have to do is show that both partials exist at 1, 0 and are continuous at 1, 0. So we're going to have to find both partials. Hopefully you can see here when you find the partial with respect to x, you're going to have to do the product rule. So we're going to get e to the xy plus xy e to the xy. If we take the first partial with respect to y, we get x squared e to the xy. What we care about is that both exist at 1, 0, which is true. Both are continuous at 1, 0. That's also true, which tells us then that f of xy is differentiable at 1, 0. Okay. Next, we need to find the linearization, which is L of xy. That's going to be f of 1, 0 plus the first partial with x at 1, 0 times x minus 1 plus the partial of y at 1, 0 times y minus 0. If you plug 1, 0 in up here, you're going to get 1. If you plug 1, 0 in here, you're also going to get a 1. If you plug 1, 0 in to the first partial with respect to y, you're still going to get a 1. So our L of xy then is x plus y. This is the linearization. When you use the linearization, it's called a linear approximation. So that f of xy, which is xe to the xy, we're going to say is approximately x plus y. This is called the linear approximation now. Or the tangent plane approximation. So we need to approximate f of 1.1 comma negative 0.1. Using the approximation, we get 1.1 minus 0.1. So we get an estimate of 1. If you actually plug 1.1 common negative 0.1 into f, you get 0.98542. I rounded it, but those are the first 5 decimal places. Okay. Do we have questions on linear approximations, differentiability, or tangent planes? It's kind of the same idea over and over again, just in a different form. Do we feel okay? Okay, so then here's the deal. We are about halfway through the notes. We can choose right now to finish the notes, and then you'll have a work day tomorrow, or we can stop now and finish notes tomorrow. Would you guys like to power through and finish the notes, or do you want to wait for tomorrow?
No.
Sure.
Okay, do we have the mental focus to get through the rest of the notes today?
Sure. Absolutely. I just write stuff down.
I don't know if I'm writing anymore, I'm writing so fast.
I'll just remember.
It's okay, I can like go back and watch the video.
Yeah. Always mentally focused.
So that's a yes? Go on.
Yes.
I don't care.
So torn. So torn. Okay. We're gonna go on. Okay. Last thing we need to talk about is the differential. Sorry, it's so dark. I don't know why it's so dark. Okay. Do you know what I mean by differential? Oh, that's not good. Okay. dy is the differential from Calc 2, and that's f prime of x dx. dx is a differential, dy is a differential. Yes? No?
Yes.
Okay.
Yes.
Whew. Okay. Let's look at this figure. Let's say that we have some curve C. Sorry, I don't know how to make it any lighter. Is it bugging you all or just me? Just me? Okay, good. That works. Okay, so here's the idea that we're going to look at. We choose some point. This is going to be the idea two-dimensionally, which you guys looked at last year, and then we're going to look at it three-dimensionally. We choose some point, and we draw in the tangent line at that point. Okay. At that point, let's call our x value a. Then we might go a little bit further along, so that'll be a add delta x. So a add whatever the change in x is. Okay. So this then is the actual y value. Okay. This right here is delta y. That is the actual change in y. That is the change in y from where I originally was to the change in y now. Do we see that? Okay. So then this little part here, that is dy. So that would be if we used our tangent line to approximate the value of y at this new x value. Do we see that this is the change now between our estimate and the actual value? So this right here then would be that little bit of error. You guys with me? Okay. This part here is dx. So dx is just the change in x. Okay, so delta y, that is the actual change in y from x equals a to x equals a add delta x. So that's what we just talked about. When I move from here to here, that delta y is the actual change in y. dy is the change in y when using the tangent line. Here's the key idea. When delta x is small, so when we don't vary too much from that initial x, dy can be used to approximate delta y. Okay. Questions yet? No? Okay. This is what you guys did last year. We're now going to do it three-dimensionally. So we're going to try to estimate the change in y when we move along with x, except we're going to do change in z. This brings us to the total differential. Okay, we are not going to go through deriving the total differential. It's related to the linear approximation, so I'm just going to tell you what it is. Total differential is dz. It's going to be the first partial with respect to x at the point xy times dx plus the first partial with respect to y times dy instead of xy, you might see the point AB. So you're going to be substituting a point in, so just know if you see AB instead of xy. It just means the point is substituted in already. Okay. This dx is going to be the real change in x, which is going to be x minus a. Same idea with dy. Okay, the linear approximation then becomes the following. F of xy is approximately going to be f of AB plus dz. Bless you. Okay, remember, dz is estimating delta z. Delta z is the real change in z. So f of xy really is f of AB plus delta z. So it's the real z value and then adding on the change in z. But instead of using delta z, we're approximating delta z with dz. Okay, here's the picture. Okay, blue is the surface itself. The orange is the tangent plane. This is the point that we're starting at. So this is the point where the tangent plane was created. We want to estimate the z value at this point. So if we use the tangent plane, we'll get a point right there. Delta z is the real change in z to the change in, well, from the point we're at to the point we're going to. dz is the estimate. It's when we use the tangent plane. See what I'm talking about? Yep. I feel like I've lost a good 2/3 of you. Okay. We're good? Okay. Some of you are giving me faces that don't say that. Johnny?
Is dy exact, or is it an approximation?
Our dx and dy, we're going to use exact values. Yes. Okay. We're going to look at some examples. I don't think it's as bad as you guys think it is. So we'll look at an example. It looks bad when you're talking about the idea behind it, but when you actually apply it, it isn't as bad as you think. Okay. We are going to look at the function xy squared. Part A, we are going to find the total differential. Okay, total differential is what we did up here, or what we wrote up there. So we need the first partial with respect to x. I'm using z because we don't have an f, we have a z. Okay, first partial with respect to x will give us y squared. First partial with respect to y will give us 2xy. So the total differential then will be dz equals y squared dx add 2xy dy. We don't have any points to plug in, so we aren't going to plug in anything yet. Next, what we are going to do is we are going to approximate the change in z when we go from the point 0.51 to the point 0.503, 1.004. Okay, so here's how this is going to work. We're going to use that total differential. X and y, you are always going to use the original x and y where you started. So this is going to be our x and y. So y squared will be 1 squared. dx is the change in x. Change in x in this case is 0.503 minus 0.5. And then we have 2xy. Again, that's the point we're starting at. dy is the change in y. So 1.004 minus 1. That ends up being 0.007. Here's what this means. When we move from this point to this point on our surface, we expect or we estimate z to increase by 0.007. Okay, I had us do another one just where we got a negative dz. What does a negative dz mean?
Z is decreasing.
Z is decreasing, yeah. And then we have one more part to do. Next, we are going to compare to the actual change. So remember that dz is an approximation. Delta z is the actual change in z. So the actual change in z we're going to find from subtracting the two z values. So we're going to plug these two values into our surface. So we have x, which is 0.503, times y squared, 1.004 squared, minus x, which is 0.5 times y squared. And that ends up being about 0.007032048. And it keeps going. So this is the actual change. This is our estimate of the change. So this is the estimate for the actual change. Okay. Questions?